In Ontario, Canada, the Electrical Safety Authority, often abbreviated as ESA, has specific requirements for ground fault circuit interrupters, or GFCIs, and arc fault circuit interrupters, or AFCIs, in residential buildings. It is important to understand the differences between these two types of protective devices and where they are required to be installed to ensure electrical safety and code compliance. Ground fault circuit interrupters, or GFCIs, are designed to protect individuals from electrical shock. They monitor the current flowing in a circuit and quickly interrupt the power if they detect a leakage current flowing to ground. This leakage current can occur when someone comes into contact with a live electrical component, providing a path for the current to flow through their body to ground. GFCIs are typically installed in areas where there is a higher risk of water exposure, as water can significantly increase the likelihood of electrical shock. According to the ESA, GFCIs are required in all bathrooms, kitchens, and finished basements, garages, and outdoor receptacles. Bathrooms are a prime location for GFCIs due to the presence of water from sinks, showers, and bathtubs. Kitchens also require GFCIs due to the potential for water exposure near sinks and dishwashers. Unfinished basements, garages, and outdoor receptacles are also considered high-risk areas due to the increased likelihood of moisture in contact with the ground. Arc fault circuit interrupters, or AFCIs, on the other hand, are designed to protect against electrical fires. Arc faults are dangerous electrical arcs that can occur due to damaged or deteriorated wiring, loose connections, or faulty appliances. These arcs generate intense heat and can ignite nearby flammable materials, leading to a fire. AFCIs detect these arc faults and quickly interrupt the power, preventing a fire from starting. The ESA mandates the installation of AFCIs in all bedrooms, family rooms, living rooms, dining rooms, kitchens, hallways, laundry rooms, and closets. These areas are considered high risk because they often contain numerous electrical appliances, cords, and wiring that can be subject to damage or wear over time. Bedrooms are particularly important to protect with AFCIs, as people are often asleep and unaware of potential hazards. Family rooms, living rooms, and dining rooms also have a high density of electrical devices and wiring, increasing the risk of arc faults. It is important to note that GFCIs and AFCIs serve different purposes and provide different types of protection. GFCIs protect against electrical shock, while AFCIs protect against electrical fires. In some cases, both types of protection may be required in the same area. For example, a kitchen countertop receptacle near a sink may require both GFCI and AFCI protection. The ESA allows for AFCIs to be installed in the electrical panel itself rather than at each individual outlet. This can be a more convenient and cost-effective option, especially in older homes where it may be difficult to rewire the entire electrical system. However, it is important to ensure that the AFCIs installed in the panel are properly rated for the circuits they are protecting. To determine the specific GFCI and AFCI requirements for a particular project, it is always best to consult the latest edition of the Ontario Electrical Safety Code and to seek guidance from a qualified electrical contractor or the Electrical Safety Authority. It is also important to remember that electrical work can be dangerous and should only be performed by qualified individuals. If unsure about working with electricity, it is always best to hire a licensed electrician to ensure the work is done safely and correctly. Ground fault protection works by monitoring the balance of current between the ungrounded or hot conductor and the grounded or neutral conductor. In a properly functioning circuit, the current flowing through these conductors should be equal. However, if a ground fault occurs, meaning current is leaking to ground through an unintended path, this balance is disrupted. A ground fault circuit interrupter, or GFCI, is designed to detect this imbalance. Inside the GFCI is a differential transformer that measures the difference in current between the hot and neutral conductors. When the difference exceeds a certain threshold, typically 5 milliamps, the GFCI trips, quickly interrupting the power to the circuit. This rapid interruption of power prevents a dangerous electrical shock. Ground fault circuit interrupters, or GFCIs, come in two main types: receptacle type and circuit breaker type. Receptacle type GFCIs are installed in place of standard electrical outlets. They have a test button and a reset button on the face of the receptacle. The test button allows the homeowner to verify that the GFCI is functioning correctly, and the reset button is used to restore power after the GFCI has tripped. Circuit breaker type GFCIs are installed in the electrical panel. They provide ground fault protection for the entire circuit. They also have a test button to verify functionality. Arc fault protection, on the other hand, works by detecting the unique characteristics of arc faults. Arc faults produce erratic current flow and high-frequency electrical noise that are not present in normal circuits. An arc fault circuit interrupter, or AFCI, uses sophisticated electronic circuitry to analyze the current waveform and detect these telltale signs of arc faults. When an arc fault is detected, the AFCI trips, interrupting the power to the circuit and preventing a fire. Arc fault circuit interrupters, or AFCIs, also come in two main types: branch circuit AFCIs and combination AFCIs. Branch circuit AFCIs protect against arc faults in the branch circuit wiring, which is the wiring between the electrical panel and the outlets. Combination AFCIs provide both branch circuit and outlet circuit arc fault protection. They are more sensitive and can detect a wider range of arc faults. When choosing AFCIs, it is important to select the correct type for the application. Combination AFCIs are generally recommended for new installations, as they provide the most comprehensive protection. However, branch circuit AFCIs may be suitable for some existing installations, especially where it is difficult to replace all of the outlets. Electrical codes, like the Ontario Electrical Safety Code, are regularly updated to reflect new technologies and safety concerns. It is essential to stay informed about the latest code requirements to ensure that electrical installations are safe and compliant. The Electrical Safety Authority, or ESA, provides resources and information on its website to help homeowners and electrical contractors understand and comply with the electrical code. This includes publications, training programs, and online tools. When planning electrical work, it is always advisable to consult with a qualified electrical contractor. A licensed electrician has the knowledge and experience to ensure that the work is done safely and correctly. They can also help you navigate the complexities of the electrical code and select the appropriate electrical devices and wiring for your specific needs. Attempting to perform electrical work without the proper training and experience can be dangerous and may result in serious injury or property damage. Moreover, non-compliant electrical installations can create fire hazards and void insurance coverage. Firstly, always disconnect the power before working on any electrical circuit. Locate the circuit breaker that controls the circuit you will be working on and turn it off. Use a voltage tester to verify that the power is off before touching any wires. Secondly, use the correct tools for the job. Using the wrong tools can damage the wiring or electrical devices and create a safety hazard. Thirdly, follow all applicable electrical codes and safety standards. The electrical code provides detailed instructions on how to safely install electrical wiring and devices. Fourthly, never work on electrical circuits when you are wet or standing in water. Water is a good conductor of electricity, and contact with water can significantly increase the risk of electrical shock. Fifthly, if you are unsure about any aspect of electrical work, seek professional help from a qualified electrician. It is always better to be safe than sorry when it comes to electricity. The Ontario Electrical Safety Code is a comprehensive set of rules and regulations that govern the safe installation and maintenance of electrical systems in Ontario. The code is based on the Canadian Electrical Code, but it also includes additional requirements specific to Ontario. The Electrical Safety Authority, or ESA, is responsible for enforcing the electrical code in Ontario. The ESA conducts inspections of electrical installations to ensure that they comply with the code. The ESA also investigates electrical incidents and takes enforcement action against those who violate the code. The electrical code covers a wide range of topics, including wiring methods, overcurrent protection, grounding, and bonding. It also includes specific requirements for different types of electrical installations, such as residential, commercial, and industrial. The electrical code is updated regularly to reflect new technologies and safety concerns. The latest edition of the code is the 2021 Ontario Electrical Safety Code. It is important to use the latest edition of the code when planning and performing electrical work. The electrical code is a complex document, and it can be difficult to understand all of the requirements. If you have any questions about the code, consult with a qualified electrical contractor or the Electrical Safety Authority. The purpose of grounding is to provide a low impedance path for fault current to return to the source. This helps to ensure that overcurrent protective devices, such as circuit breakers and fuses, will trip quickly in the event of a ground fault. Grounding also helps to reduce the risk of electrical shock by providing a safe path for current to flow in the event of a fault. Bonding is the process of connecting all of the metal parts of an electrical system together to create a continuous electrical path. This helps to ensure that all metal parts are at the same electrical potential, which reduces the risk of electrical shock. Bonding is also important for reducing electromagnetic interference. Common types of wiring include non-metallic sheath cable, often referred to as NM cable or Romex, armored cable, often referred to as AC cable or BX cable, electrical metallic tubing, often referred to as EMT, rigid metal conduit, and liquid-tight flexible metal conduit. Non-metallic sheath cable is the most common type of wiring used in residential construction. It consists of 2 or more insulated conductors wrapped in a plastic jacket. Armored cable consists of insulated conductors wrapped in a flexible metal sheath. Electrical metallic tubing is a thin-walled metal conduit that is used to protect conductors. Rigid metal conduit is a thick-walled metal conduit that is used to protect conductors in harsh environments. Liquid-tight flexible metal conduit is a flexible metal conduit that is used to protect conductors in wet locations. The size of the wire required for a particular circuit depends on the ampacity of the circuit. Ampacity is the maximum amount of current that a conductor can carry safely without overheating. The electrical code specifies the ampacity of different sizes of conductors. It is important to use the correct size of wire for a circuit to prevent overheating and fire hazards. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from overloads and short circuits. Overloads occur when a circuit is carrying more current than it is designed to handle. Short circuits occur when there is a direct connection between 2 conductors of different voltage. Overcurrent protection devices trip or blow when the current in a circuit exceeds a certain level. This interrupts the flow of current and prevents damage to the wiring and electrical devices. Circuit breakers are reusable overcurrent protection devices. They trip when the current in a circuit exceeds a certain level, and they can be reset after the fault has been cleared. Fuses are one-time overcurrent protection devices. They blow when the current in a circuit exceeds a certain level, and they must be replaced after they have blown. The choice between using circuit breakers or fuses depends on the specific application and the preference of the electrician. Always consult the electrical code and follow the manufacturer's instructions when installing electrical wiring and devices. Electrical work can be dangerous and should only be performed by qualified individuals. If you are unsure about any aspect of electrical work, seek professional help from a qualified electrician.